Right now, about 20,000 kilometers above your head, there are roughly 30 machines running on clocks that were deliberately built to keep the wrong time. Before each one launched, a technician detuned it by about 4.5 thousandths of a hertz so that it would run slow on the workbench and correct in orbit. It has to be done that way. Up there, time genuinely runs faster, about 38 microseconds a day faster. And if nobody had corrected for it, your phone's idea of where you are would drift by 11 kilometers every single day. So the sentence people say without ever thinking about it, that time travel is impossible, is being quietly contradicted by a fleet of satellites built on the opposite assumption, which have worked flawlessly for 30 years. But here is what gets left out. That is only one of 3 separate claims hiding inside the word impossible. One of the other 2 turns out not to be a claim about physics at all, and the last one rests on something its own author called a conjecture. Get comfortable. Hit subscribe if you're new here, because by the end of tonight, you will know exactly why time travel is not as impossible as you think, and the reason has nothing to do with wormholes. Now, let's slowly ease into this. Part 1. The clock that was built wrong on purpose. Somewhere in a clean room, right now, somebody is deliberately building a clock that does not keep the correct time. It is a small thing, roughly the size of a shoebox, and it will spend the next 15 years about 20,200 kilometers above your head. Before it is bolted into the satellite that will carry it there, a technician adjusts its oscillator downward by a very precise amount. The frequency should be 10.23 MHz. It is set instead to 10.2299999543 MHz. The difference is about 4.5 thousandths of a single hertz, which is a fantastically small change to make to something that has been engineered for accuracy at the level of parts in 10 to the 14th. On the bench, at sea level, that clock is now wrong. It is wrong through integration. It is wrong through the launch campaign. It is wrong sitting on the pad in Florida in the heat. And then, roughly 12 minutes after the upper stage separates and the satellite settles into its orbit, it becomes right, and it stays right for the rest of its working life. Nobody in that clean room finds this strange. It has a name in the engineering documents. It is called the factory offset, and it has been standard practice on every single global positioning system satellite ever flown. There is a technician somewhere who has spent a career detuning clocks so that they will run correctly somewhere else, and to that person, this is Tuesday. The reason the offset exists is that time does not run at the same rate at the top of that orbit as it does at the bottom of your street, and the difference is large enough to break the system if you ignore it. 2 separate effects are in play, pulling in opposite directions. The satellite is moving at about 3.87 kilometers per second, and motion slows a clock down. That costs about 7 microseconds a day. The satellite is also higher up, where the Earth's gravitational pull is weaker, and being higher in a gravitational field speeds a clock up. That gains about 45 microseconds a day. 45 minus 7 leaves 38, and so every atomic clock in the constellation runs 38 microseconds a day, fast relative to the ones on the ground. 38 microseconds sounds like nothing. It is nothing in the sense that you have never experienced a duration that short and never will. But the system works by timing radio signals traveling at the speed of light, and light covers about 300 meters in a microsecond. 38 microseconds is about 11 kilometers. Left uncorrected, the position your phone reports would drift by roughly the width of a city every single day, and it would keep drifting. So the correction is not applied afterward. It is built in beforehand, at the factory, into the hardware, by a person with a screwdriver. It was contested, incidentally, before the first launch. The relativistic prediction was not universally trusted inside the program. So the very first Block 1 satellite carried a frequency synthesizer that would let the engineers switch the correction off if the physicists turned out to be wrong. They ran it for about 20 days. Then they switched the correction on and never looked back. I want to sit on this for a moment because of what it means for the question we came here to ask. If you say to almost anyone that time travel is impossible, they will agree with you immediately and without hesitation. It is one of those statements that feels less like a claim and more like a description of the furniture, and yet the sentence has a very specific problem, which is that there is a fleet of 30-odd machines in orbit whose clocks were manufactured incorrectly on purpose, because the engineers who built them accepted that time runs at a different rate up there, and designed around it, and shipped it. Those satellites are traveling into the future faster than you are, not metaphorically, measurably, in nanoseconds, in a quantity that has to be subtracted, or the whole thing falls apart. And this is not the only place we have measured it. In October of 1971, two physicists named Joseph Hafele and Richard Keating took 4 cesium beam atomic clocks and bought them seats on ordinary commercial airliners. Not cargo, seats, booked and paid for. They flew the clocks around the world twice, once heading east and once heading west, and then compared them against the reference clocks at the United States Naval Observatory. Relativity predicted the eastward clocks should lose about 40 nanoseconds, plus or minus 23, and the westward clocks should gain about 275, plus or minus 21. What they measured was a loss of 59 nanoseconds, plus or minus 10, going east, and a gain of 273, plus or minus 7, going west. The part of that result which is hard to argue with is not the size of the numbers. It is the sign flip. The clocks going east disagreed with the ground in one direction, and the clocks going west disagreed in the other, because the Earth itself is turning, and turning eastward adds to your speed, while turning westward subtracts from it. A faulty clock does not know which way the aeroplane is pointing. The whole experiment, airfare included, cost somewhere in the region of $8,000, which probably makes it the cheapest confirmation of general relativity anybody has ever performed. Then there are the people. The cosmonaut Sergei Krikalev spent 803 days, 9 hours and 39 minutes in orbit across 6 separate spaceflights. At the orbital speed of the station, about 7.66 kilometers per second, the accumulated difference between his clock and everyone else's works out to roughly 2/100ths of a second. He came back about 1/50th of a second younger than he would have been if he had stayed home. Gennady Padalka later passed him on total days, 878, and gained a slightly bigger offset, about 2.5 That is a very small number, and I do not want to oversell it. But it is not zero, it is not a rounding error, and it is not a theory. It is the largest deliberate displacement of a human being into the future that has ever been achieved, and it is in the record, and the man who did it is alive and can be asked about it. The effect shows up in particles too, and there it is enormous. Cosmic rays hitting the upper atmosphere create muons at an altitude of around 15 kilometers. A muon at rest survives for about 2.197 microseconds before it decays. Even traveling at nearly the speed of light, that lifetime should carry it about 660 meters, nowhere near the ground. And yet muons arrive at sea level at a rate of about 1 per square centimeter per minute. They arrive because from their point of view the trip is short, and from ours, their clocks are running slow. At CERN's muon storage ring, the lifetime extension was measured directly at a factor of 29.3, and it agreed with the prediction to about 1 part in 1,000. And the measurement has now become so fine that it has stopped being an experiment about spaceflight at all. In 2022, a team at Gila in Colorado, led by Tobias Bothwell, published a result in Nature. They took a cloud of ultra-cold strontium atoms about 1 millimeter tall and measured the difference in tick rate between the top of the cloud and the bottom. 1 millimeter. The fractional frequency uncertainty was 7.6 times 10 to the minus 21st, which is a number I am not going to pretend anybody has an intuition for. The point is that gravitational time dilation is no longer something you go to orbit to observe. It is now a correction that clock builders have to apply across the width of their own sample, on a bench, in a room. So we have a situation. One kind of time travel is not merely possible. It is measured, engineered, industrialized, and running quietly overhead while people on the ground say it cannot be done. Which raises an obvious question, and it is the question this whole video is going to spend the next 2 hours taking apart. If that is what the word impossible does not cover, then what exactly does it cover? Because when people say time travel is impossible, they are clearly not talking about any of this. They are talking about something else, and they are extremely confident about it, and almost nobody has ever stopped to ask what the something else actually is. Part 2. What the word is actually carrying. Here is a small experiment you can run in your own head. Say the sentence, "Time travel is impossible," and then ask yourself which part of it you actually believe. Most people, pressed on this, will not defend the forward direction. Once you point out the satellites and the cosmonauts and the muons, they will concede that bit quite cheerfully, usually with a shrug, because it does not feel like the thing they meant. And they are right. It is not the thing they meant. The word impossible, in that sentence, is carrying 3 completely separate claims at once, stacked on top of each other like coins, and the whole weight of the sentence is resting on whichever one you happen to touch. The first claim is that moving through time at a rate different from everybody else's cannot be done. We have just spent 20 minutes establishing that this one is simply false, and has been known to be false since 1905. It is not controversial, it is not marginal, and it is not new. It is in the hardware. The second claim is that the past no longer exists, and therefore there is nowhere to arrive. This is the one people mean. This is the actual objection, and it is worth saying it out loud in its strongest form, because it is genuinely a good objection. The argument goes, even if you could somehow get a machine to point the other way, what would it be pointing at? 1972 is not a location. Nobody is there. It is not a place that has been abandoned. It is a place that has stopped being. Asking to travel to it is like asking to travel to the shape of a cloud you saw last Thursday. The problem is not that the journey is difficult. The problem is that the destination has been deleted. The third claim is that going backward is forbidden by the laws of physics, that there is a rule against it, that somewhere in the equations there is a term, a sign, a theorem with somebody's name on it that closes the door. 3 claims. And they get used interchangeably, which is where the confidence comes from. Somebody challenges the third one, and you fall back on the second. Somebody challenges the second, and you appeal vaguely to the first. The sentence survives every attack because it is never in the same place twice. So I want to do something slightly unusual with the next 2 hours, which is to take the 3 of them apart separately and see what each one is actually standing on. The first one, as we have established, has already fallen over. That is settled, and we can leave it behind. The second one is going to turn out not to be a claim about physics at all. It is an intuition, a very strong one that everybody has, one that feels like it was handed down with the rest of the furniture of the world. And it is the intuition that relativity contradicts more directly than almost anything else it touches. That is where we are going next, and it is going to take a while, because the argument is subtle, and I do not want to rush it. The third one is the interesting one, and I am going to be honest with you now about where it ends up, because I would rather you trusted me for 2 hours than felt tricked at the end of them. The third claim is genuinely open. It is not settled in either direction, but it is not settled in the direction you were told. There is no theorem, there is no proof. What there is instead is a conjecture, and I mean that word in its formal sense, the sense in which a mathematician uses it, and I will show you the paper where the man who proposed it put the word conjecture in his own title. And alongside that conjecture there is a bill, a very large, very specific, very carefully calculated bill, denominated in a kind of matter that we know exists and cannot make in quantity. That is the shape of where we are heading. A measured fact, an intuition, and a conjecture with a price tag. But I am not going to give you the answer yet, and I want to be upfront about that too, because the answer only lands if you have walked the whole distance to it. There is a specific reason why time travel is not as impossible as you think, and it is not the reason you are probably expecting. It is not a loophole, it is not a clever trick with wormholes, and it is not a discovery that somebody made last year. It is something much stranger and much older, and it has been sitting in the literature in plain sight for the better part of a century, published, peer-reviewed, uncontested, and almost entirely unmentioned outside a fairly small room of specialists. By the end of tonight, you will know exactly what it is. For now, hold on to the second claim, because everything hinges on it. There is nowhere to arrive. That is the sentence. That is the whole objection, in 7 words. Remember it, because we are going to come back to it, and when we do it, is not going to look the way it looks right now. And to get there, we have to start by taking apart a word that seems so obvious it has never needed defending. Not past, not future. Now. Part 3. The destruction of the universal now. There is a word you have used every day of your life without ever once inspecting it, and it does not survive inspection. The word is now. And what you mean by it, without ever having decided to mean it, is something like this. There is a moment, this moment, and it extends outward from you in every direction, and everything in the universe is either in it or not in it. The moon is in it. The far side of the sun is in it. A rock on a planet orbiting a star in the Andromeda galaxy is in it, doing whatever it is doing, right now, at the same time as you sitting there. Not that you could see it. Light takes time, but the seeing is a separate problem from the being. The rock is doing something now. There is a fact of the matter about what. That picture is wrong, and it has been known to be wrong for 120 years. And the reason it is wrong is almost embarrassingly simple once you see it. Start with the thing everybody has heard. Light always travels at the same speed. Not the same speed relative to its source, or relative to whoever is watching. The same speed, full stop, no matter who measures it, or how fast they happen to be moving when they do. This is not a philosophical position. It is what the measurements say, and they have said it consistently since the 1880s, and every attempt to make it not be true has failed. Now follow what that force is. Imagine 2 events, some distance apart, 2 lamps switching on, say, one at each end of a long hall. You are standing exactly in the middle. The light from both lamps reaches you at the same instant. You conclude, quite reasonably, that they switched on at the same time, simultaneous. Now, put somebody else in the hall, walking steadily from one end toward the other. Same lamps, same 2 flashes of light, same speed for both. But she is moving toward one lamp and away from the other, while the light is in transit. So the light from the lamp she is walking toward reaches her first. She concludes that lamp switched on earlier. And here is the part that matters. She is not making a mistake. There is no correction she has failed to apply, no perspective she needs to adjust for. If the speed of light is the same for both of you, and it is, then her conclusion is as valid as yours. The 2 lamps switched on at the same time in your accounting, and at different times in hers, and there is no third accounting that settles it, because there is no privileged place to stand. There is an objection that almost everybody raises at this point, and it is worth killing properly, because if it survives, nothing else in this video works. The objection is, surely she is just seeing it late. Surely the lamps did switch on at the same time, and she is simply badly placed, and if she did the arithmetic, subtracted the travel time for each beam, accounted for her own motion, she would get the same answer you did. She would not. And the reason is the thing about light that we started with. If she measures the speed of the light coming from in front of her and the speed of the light coming from behind her, she gets the same number for both, even though she is closing on one beam and running from the other. That is not intuitive, and it is not negotiable. It is the measured result. So when she does the arithmetic and divides the distances by the speed, she gets different transit times than you would assign, and she arrives at different emission times, and her arithmetic is correct. The disagreement is not an artifact of signal delay that careful bookkeeping removes. The careful bookkeeping is what produces it. Einstein's own version of this used a train and an embankment and 2 lightning strikes, and he was quite deliberate about the setup. He insisted that both observers be equipped to do the calculation properly, precisely so that nobody could dismiss the result as an illusion of position. Once both of them have done it right, they still disagree, and that is the whole point of the example. This is called the relativity of simultaneity, and Einstein put it in the 1905 paper. And it is not a curiosity tucked away in a corner of the theory. It is the theory. Everything else, the time dilation, the length contraction, the mass-energy equivalence, falls out of this one observation once you follow it properly. And the consequence for the word now is total. There is no universal moment. What you are calling now is a slice you have cut through the 4-dimensional world, and the angle of that cut depends on how you are moving. Somebody moving differently cuts at a different angle, and their slice contains different events than yours does. Here is the arithmetic, because the arithmetic is where this stops being a philosophical puzzle and starts being a physical fact with a number attached. The offset between 2 observers' notions of simultaneity, out at some distance, is given by a very short formula, the relative velocity multiplied by the distance divided by the speed of light squared. That is it. Velocity times distance over c squared. Notice what that formula does. The velocity term is small in ordinary life. Walking pace is about 1.5 meters per second, which is nothing, and c squared in the denominator is enormous, about 9 times 10 to the 16th. So for anything nearby, the offset is unmeasurably tiny. 2 people passing each other on a street disagree about the simultaneity of events in the next room by something like 10 to the minus 17 seconds. Nobody is going to notice. But look at that distance term. It is not divided by anything. It multiplies. Which means that if you make the distance large enough, a walking pace will do. The Andromeda Galaxy is about 2.5 million light-years away, which is roughly 2.4 times 10 to the 22nd meters. Suppose you are standing still, facing it. There is some set of events happening in Andromeda that your slice of the universe calls now. Now take one slow step toward it. One step. Walking pace, 1.5 meters per second. The kind of thing you do without thinking on the way to the kitchen. Your plane of simultaneity out at Andromeda has just swung by about 370,000 seconds. That is around 4 1/3 days. Take a step backward and it swings the other way, by the same amount. Stand still, step forward, step back, and the moment in Andromeda that you are calling now slides by more than a week, back and forth, at the speed of your own feet. I want to be very careful about what this does and does not mean, because it is easy to oversell, and I am not going to. Nothing in Andromeda changes when you take a step. You have not influenced anything. You could not send a message there, or receive one, or learn anything about the place at all. The events in question are what physicists call space-like, separated from you. which means no signal, no light, no causal influence of any kind can pass between them and you. They are outside your light cone. They are, in the geometry, in a region that is neither your past nor your future, and relativity has a name for it, the elsewhere. What has changed is which events you are calling now. And since the answer depends on something as trivial as whether you took a step, the honest conclusion is that now is not a property of the universe. It is a property of your motion through it. It is a choice of coordinate, in the way that calling one direction north is a choice of coordinate. That was the argument that Roger Penrose used to make with a thought experiment about two people walking past each other on a street, and it is the argument that Wim Rietdijk in 1966 and Hilary Putnam in 1967 wrote up independently and turned into a formal claim about the nature of reality. It has been argued over ever since. Howard Stein published a serious objection in 1968, pointing out that the argument needs a notion of one event being real for a distant observer, and that relativity does not actually hand you that notion. The debate is still going. I am not going to tell you it is settled, because it is not. But strip out the philosophy, and one thing remains, and it is the thing we are here for. If there is no universal now, then there is no universal past either. The two are the same claim, wearing different clothes. The past is defined as everything before the present moment, and if the present moment is a slice whose angle depends on how you happen to be moving, then what falls behind that slice depends on it too. Which means the objection we are chasing, there is nowhere to arrive, the past is gone, has just acquired a problem it did not have 5 minutes ago. Gone according to whom, cutting at what angle, moving at what speed? Because right now, somewhere, moving differently to you, there is somebody whose slice of the universe puts your yesterday squarely in their present. Part 4. The Past as a Place. In September of 1908, a mathematician named Hermann Minkowski stood up in Cologne to give a lecture, and he opened it with a sentence that people are still quoting 117 years later. Space by itself, he said, and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Minkowski had been Einstein's mathematics teacher in Zurich, and by his own account had not been especially impressed by the student at the time. What he had spotted, 3 years after the 1905 paper, was that the whole of special relativity becomes almost trivially simple if you stop treating space and time as two separate things and start treating them as one four-dimensional object. This is not an interpretation of relativity. It is not a way of thinking about relativity that some people find helpful. It is the mathematics of relativity. Every calculation in the theory is done in Minkowski's four-dimensional geometry, and the reason the theory works is that the four-dimensional description is the one where the quantities stop depending on who is looking. That last point is the key to everything that follows, so let me put it plainly. In relativity, two observers moving differently will disagree about how far apart two events are in space. They will disagree about how far apart they are in time. But there is a combination of the two. The space-time interval, distances measured one way, times measured the other, subtracted rather than added, and every single observer, no matter how they are moving, calculates the same value for it, always. That invariant quantity is the thing relativity says is real. The separate space part and the separate time part are the shadows Minkowski was talking about. They are projections. They depend on the angle you cut at. Now hold that alongside what we established a few minutes ago. Your now is a slice through this four-dimensional object, and its angle depends on your motion. And somebody moving differently slices at a different angle and gets a different set of events. Put those two together, and you arrive somewhere that most people find quite hard to sit with. If the four-dimensional object is what exists, if that is the thing relativity is describing, and the slices are just cuts we make through it, then all of it exists. Not sequentially, not one bit at a time, with the rest waiting or discarded. The whole four-dimensional extent, the way a map exists all at once, even though you walk across the territory one step at a time. Philosophers call this eternalism, and physicists mostly just call it the block universe. And the picture it gives you is this. You are not a point moving along a line. You are the line. Think about it that way for a moment, because it takes a while to settle. Everything you have ever been is at its coordinates. The child you were is at a set of coordinates in that structure, doing what children do, permanently. The person you were 10 minutes ago is at their coordinates. The person you will be tomorrow morning is at theirs. None of these is a memory of something deleted or a forecast of something not yet made. They are regions of an object, the way the far end of a road is a region of the road, even when you are standing at this end of it. And the sense you have of moving through it, of a present that slides forward and leaves a wake of vanished moments behind it, is on this picture a fact about you rather than a fact about the world. You are a creature with memory, embedded in the structure, and the structure at each of your coordinates contains a brain that has records of the coordinates behind it and none of the ones ahead. Of course it feels like flowing. There is no configuration of that arrangement that would feel like anything else. There is a worry that arrives with this picture almost immediately, and it is worth disposing of before it grows, because it is not the worry people think it is. The worry is that if tomorrow already sits at its coordinates, then nothing you do matters. The future is fixed, your choices are theatre, and the whole thing collapses into fatalism. That does not follow, and the reason is quite simple. The block picture says the future exists. It does not say the future exists independently of what you do. You're deliberating, you're weighing it up, you're changing your mind at the last second. All of that is part of the structure too, sitting at its own coordinates, doing exactly the causal work it appears to do. The road ahead being there is not the same as the road ahead being there, regardless of how you drive. What eternalism removes is the metaphysical distinction between the parts of the structure, not the causal relations inside it. That is a genuinely separate argument, and people have written whole books on it. I raise it only to set it aside, because it is not what we need the block for tonight. I want to run the Andromeda demonstration one more time, but physically now, with you in it, because it is different when you put yourself inside the geometry rather than looking at it on a diagram. You are standing still, face the direction of Andromeda. It does not matter that you cannot see it. There is a slice of the universe you are calling now, and out there, 2.5 million light-years away, it picks out some particular moment, some particular arrangement of gas and stars. Take one step forward, slowly. The slice tilts. Out at that distance, the moment you are now calling now has moved forward by about 4 1/3 days. 4 days of that galaxy's history have crossed from what you call the future into what you call the past, and the only thing that happened is that your foot moved. Step back. It tilts the other way. Those 4 days cross back. Nothing out there has changed. No signal has passed. You could not affect that galaxy, and it could not affect you, and the two of you are sealed off from each other completely. Those events are in the region relativity calls the elsewhere, outside your light cone in both directions, causally unreachable in principle and not just in practice. And yet the question of which of those moments is happening now is answered differently depending on whether you are standing still or walking, and there is nothing in the physics that says one answer is the correct one. If a fact about reality can be changed by taking a step, it was not a fact about reality. That is the argument. Wim Reetdijk wrote it up in 1966, and Hilary Putnam wrote it up independently in 1967. And I said earlier that Howard Stein published a serious objection to it the following year. And I meant it. This is contested ground among people who think about it professionally. And anybody who tells you eternalism is simply proven is going further than the physics goes. Presentism, the view that only the present moment exists, is still defended. It just has a very hard job in a relativistic setting, because it needs there to be one correct slicing of space-time, and relativity does not supply one. The same difficulty sinks the halfway position, the growing block, where the past and present exist, and the future does not, for exactly the same reason, growing according to whose slice. What is not contested, by anybody, is the geometry. The four-dimensional object is how the theory is written. The disagreement is about what the object means. And there is one letter, more than any equation, that shows what it can mean to someone. In March of 1955, Michele Besso died. He had been Einstein's closest friend since their student days in Zurich, the man he worked beside at the patent office in Bern, the only person thanked by name in the 1905 paper on special relativity, the paper that started all of this. Einstein was 76 and knew he was dying himself. He wrote to Besso's family, and in the letter he wrote this, that for those of us who believe in physics, the distinction between past, present and future is only a stubbornly persistent illusion. He died 4 weeks later, on the 18th of April. I have seen that line used as a piece of decoration more times than I can count, usually stripped of everything around it. It is worth putting back. This is a very old, very ill man, writing to a grieving family about somebody they have both just lost, and what he reaches for is the geometry of his own theory, not as a metaphor, not as a comfort he does not himself believe. He says believing physicists, and he counts himself among them, and the consolation he is offering is that the distinction is an illusion, that Besso has not been deleted, because deletion is not a thing the structure does. Whether he was right is exactly what is at issue. I am not going to tell you that he was. But notice what has happened to our second claim in the last half hour. The claim was, there is nowhere to arrive, the past is gone, the destination has been deleted, the question is not hard, but empty. That claim requires a universe in which the present moment is the only thing that exists, and everything behind it has ceased. And the best-tested physical theory we have does not describe a universe like that. It describes a four-dimensional structure in which your yesterday sits at its coordinates, in which somebody moving differently right now has your yesterday inside their present, and in which the sense that it has gone anywhere is a report about your memory rather than a report about the world. That does not make the past reachable. I want to be extremely clear about that, because it is the most common way this argument gets abused. Existing is not the same as being accessible. Antarctica exists and you are not there, but it changes what kind of problem we are dealing with. We came in thinking the destination had been deleted. It has not been deleted. It is somewhere, in the only sense of somewhere that relativity is willing to give us. And the question of whether anything can get to it is suddenly not a question about metaphysics at all. It is a question about roots, which means we can finally go and look at whether the equations contain any. Part 5. The theorem that was never written. There is a phrase in general relativity that sounds like something out of a novel and is actually a piece of technical vocabulary with a precise definition. It is called a closed time-like curve. A time-like curve is just the path an ordinary object takes through space-time. You are on one right now. It is called time-like because it stays inside the light cone at every point, which is the geometric way of saying that the object never travels faster than light, never violates a single local law, never does anything even slightly unusual from its own point of view. A closed time-like curve is one of those paths that comes back to where it started, not to the same place, to the same event, same location, same moment. The object follows it perfectly normally, obeying every local rule at every instant, never exceeding light speed, never noticing anything strange, and arrives at its own past. The important thing to understand about closed time-like curves is where they come from. They are not something anybody added to general relativity to make time travel work. Nobody sat down to design them. They fall out of the equations, and they have been falling out of the equations for 100 years, usually to the considerable annoyance of the people who found them. The first one was found in 1924 by Cornelius Lanczos and worked out more fully in 1937 by Willem Jacob van Stockham. It describes an infinitely long cylinder of dust, rotating. It is an exact solution of Einstein's field equations, which means it is not an approximation, or a model, or a sketch. It satisfies the equations precisely. What neither Lanczos nor van Stockham noticed is that the solution contains closed time-like curves. Nobody noticed for 37 years. The one that got everybody's attention came in 1949 in Reviews of Modern Physics, Volume 21, page 447. The author was Kurt Gödel, who was not a physicist at all. He was the logician who had, 18 years earlier, proved that any sufficiently powerful formal system contains true statements it cannot prove, arguably the most consequential result in the history of mathematics. He was also, at that point, Einstein's daily walking companion at Princeton, and the paper was written as a birthday present. Gödel's universe rotates. It does not expand. It is filled with pressureless dust and has a negative cosmological constant. And it is homogeneous, meaning it looks the same everywhere. And through every single point in it, there passes a closed, time-like curve. Not in some exotic corner. Everywhere. In Gödel's universe, from any event whatsoever, you can in principle fly a rocket on a perfectly ordinary trajectory and return to your own departure. Einstein's published response to this is one of the more remarkable documents in 20th century physics, because he does not dismiss it. He concedes the problem is real. He says the question of whether such solutions should be excluded on physical grounds will be interesting to weigh, and he admits, and this is the part that matters, that he had been troubled by exactly this possibility since he first wrote down the field equations in 1915. He had known for 34 years that his own equations might not forbid it, and had not found a way to make them. Now, the Gödel universe is not our universe, and I am not going to pretend otherwise. Ours expands, and Gödel's does not, and the specific property his solution depends on, an overall rotation of the cosmos, has been looked for and not found. The Planck satellite data, analyzed by Daniela Sade and colleagues and published in Physical Review Letters in 2016, bounds the universe's rotation rate relative to its expansion rate at less than 4.7 parts in 100,000 million. Whatever our universe is doing, it is not Gödel's. But that was never the point of the paper, and Gödel knew it. The point is that the field equations permit the geometry. If the laws of physics forbade closed time-like curves, there could not be an exact solution containing them. There is one. There are several. There is a detail in Gödel's solution that is worth having, because it is the kind of thing that makes the whole subject feel less like philosophy and more like engineering. The loops are not tight. There is a critical distance, now called the Gödel radius, and inside it, no closed time-like curve passes. To make the trip, you have to travel out past that radius first, and only then can you come back around. For a universe with roughly our matter density, the Gödel radius works out at something in the region of 10,000 million light-years. Which is to say, even in a universe explicitly built to allow travel to the past, the itinerary is absurd. That is the first appearance of a pattern we are going to see again and again tonight, and I want you to start watching for it. The geometry says yes. The bill says something else. Gödel himself took his own result in a direction that made almost everybody uncomfortable. He did not treat it as a curiosity. He argued in his contribution to the big Einstein volume that came out a few years later, that if such universes are possible at all, then time as we ordinarily conceive it, a thing that passes, a thing that is real, cannot be a fundamental feature of reality. He was reportedly disappointed that Einstein treated the solution as a technical problem to be contained rather than as the metaphysical demolition Gödel intended it to be. In 1963, Roy Kerr published a 2-page paper in Physical Review Letters describing the geometry around a rotating black hole. This is not a contrived construction. It is the solution that describes essentially every real black hole in the sky, because essentially every black hole rotates. Deep inside it, past the inner horizon, in the region around the ring-shaped singularity, the angular coordinate stops behaving like an angle and starts behaving like time. Closed time-like curves exist in there. Kerr does not mention them. They were not what he was looking for. There is an honest caveat attached to that one, and I am going to give it to you, rather than let you find it later and feel misled. The inner horizon of a rotating black hole, the boundary you would have to cross to reach that region, is thought to be unstable. Light and matter falling in from outside get compressed against it, and their energy density runs away, a process called mass inflation, worked out by Eric Poisson and Werner Israel in 1990. If that is right, the causality-violating interior may never be reachable, because the horizon that guards it tears itself apart as soon as anything approaches. That is a real objection. It is also an objection that applies to exactly one of these 6 solutions and says nothing whatsoever about the other 5. In 1974, Frank Tipler published a paper in Physical Review D showing that Van Stockham's rotating cylinder permits a closed time-like line connecting any 2 events in the entire spacetime, and conjectured that a finite cylinder would do the same. In 1988, Michael Morris, Kip Thorne, and Ulvi Yurtseva published the paper that changed the field, and I will come back to that one properly later because it is the hinge of the entire subject. In 1994, Miguel Alcubierre published a metric in classical and quantum gravity that compresses space in front of a ship and expands it behind, allowing arbitrary effective speed, and superluminal effective travel automatically implies frames in which the trip runs backward in time. In 1993, and again in 2005, Amos Ori built toroidal vacuum solutions specifically designed so that the causality-violating region contains nothing exotic at all. 6 independent routes, found over 70 years, on 4 continents, by people who in several cases were visibly unhappy to have found them. And here is what I want you to notice, because it is the load-bearing fact of this entire video. There is no theorem. In a mathematical subject, when something is forbidden, somebody proves it is forbidden. That is what a theorem is. General relativity is full of them. Birkhoff's theorem, the singularity theorems of Penrose and Hawking, the no-hair theorems for black holes. When relativity says no, it says no with a proof, and the proof has an author and a date and a journal. Nobody has ever proved that general relativity forbids closed time-like curves. Not because nobody tried. People have been trying since 1949, and Einstein was worried about it in 1915, and the best anyone has managed in all that time is a conjecture. I want to be careful with that word, because it does specific work. In mathematics, a conjecture is not a weaker way of saying a result. It is a statement somebody believes and cannot demonstrate. It is a sentence with a question mark hidden somewhere inside it, no matter how confidently it gets repeated. Hold on to that, because in about an hour we are going to look at the conjecture in question, and at the man who proposed it, and at the word he chose to put in his own title. But first, there is an objection standing between us and any of this, and it is the objection everybody reaches for, and it is the one everybody is most confident about. It involves a grandfather. Part 6. The Paradox That Isn't. Everybody knows the grandfather paradox, and almost nobody knows what happened when physicists actually sat down and did the arithmetic on it. The setup is familiar. You travel to the past and prevent your own grandfather from meeting your grandmother. Therefore, your parent is never born. Therefore, you are never born. Therefore, you never travel to the past. Therefore, your grandfather is not prevented. Therefore, you are born and travel to the past and prevent him, and the whole thing chases its own tail forever. The conclusion everybody draws is that time travel must be impossible, because permitting it produces a logical contradiction, and the universe does not do contradictions. That reasoning is not wrong exactly. It is just answering a different question from the one people think it is answering. What the paradox actually establishes is that certain histories are not possible. It does not establish that time travel is not possible. Those are different statements, and the distance between them is where the real physics lives. The principle that closes the gap is usually named after Igor Novikov, and it goes by the rather grand title of the self-consistency principle, though it is much less exotic than it sounds. It says, "The only histories that happen are the ones that are self-consistent. That is it." That is the whole principle. And notice that this is not a new law of nature bolted onto physics to protect the timeline. It is a restatement of what the word solution means. When you solve any equation in physics, you are looking for a configuration that satisfies all the constraints simultaneously. A configuration that contradicts itself does not satisfy them. It is not a solution that gets rejected for being paradoxical. It is not a solution at all. In the same way that a number, which is both 3 and 4, is not a number that gets rejected. It is just not a thing. So the question a physicist asks is not, what happens if you shoot your grandfather? The question is, do self-consistent solutions exist at all in a space-time with closed time-like curves? Because if none do, time travel really is dead. And if they do, the paradox was never an argument about anything. In 1990, John Friedman and colleagues published a paper in Physical Review D on the Cauchy problem in spacetimes with closed time-like curves, and found that for a broad class of physical systems, self-consistent solutions exist. And then in 1991, Fernando Echeverría, Gunnar Klinkhammer, and Kip Thorne published the cleanest possible version of the test, also in Physical Review D, Volume 44, page 1077. Instead of a grandfather, they used a billiard ball, which has the advantage of obeying laws simple enough to solve exactly. Picture the table. It is a green baize table with 2 holes in it, and the holes are the 2 mouths of a wormhole. Anything that goes into the right-hand hole comes out of the left-hand hole 3 seconds earlier. That is the whole apparatus. Now you take a ball and you roll it, aiming carefully, on a trajectory that will carry it straight into the right-hand hole. The ball rolls, and before it gets there, something comes out of the left-hand hole and hits it. And the something is the same ball, 3 seconds older, arriving from its own future to knock its younger self off course. This is the paradox, laid out in brass and ivory. If the older ball knocks the younger one aside, the younger one never reaches the hole, so the older one never emerges, so nothing knocks the younger one aside, so it does reach the hole. Here is what Echeverría, Klinkhammer, and Thorne found. The collision is a glancing one. The older ball clips the younger ball, deflecting it slightly. Not enough to stop it, just enough to change its angle. It still goes into the hole. It goes in at a slightly different angle from the one you aimed at, and it comes out of the other hole, traveling on exactly the path required to deliver that glancing blow. The history closes. It is completely consistent. Nothing has been prevented, and nothing needed to be prevented. The ball's own future was always part of what determined its trajectory, and the trajectory it ends up on is the one that produces the future that produced it. That is not the interesting result. The interesting result is what happened when they tried the other trajectories. They looked at initial shots across the whole range, and for essentially every one they tried, self-consistent solutions existed. And for a very large class of them, there was not one self-consistent solution. There were infinitely many. Sit with that, because it is the opposite of what the paradox predicts. Everybody expects the problem to be that no history works. The problem is that too many of them do. You set up the initial conditions, the ball, the angle, the speed, everything you can specify before the experiment starts, and the equations return an infinite family of futures, all of them perfectly consistent, and nothing in the initial data to tell you which one you get. The technical way to say this is that the Cauchy problem is not well posed. The plain way to say it is that determinism breaks, not by producing a contradiction, which is what everyone was braced for, but by producing an embarrassment of riches. The universe knows how to be consistent. It just does not seem to know how to be unique. Igor Novikov and Elena Mikheeva ran the numbers again in 1993 for relativistic billiards and got the same answer. Consistency, yes. Uniqueness, no. The obvious objection, and people made it immediately, is that a billiard ball is not a person. A ball cannot decide to aim for a paradox. So the skeptics constructed the hardest version they could. Rig the apparatus so that the emerging ball is guaranteed to knock the younger ball completely away from the mouth. A bomb, effectively, wired to make consistency impossible. What comes out of the analysis in those cases is not a contradiction. It is that the setup is not an allowed initial condition. You cannot specify it. In the same way that you cannot specify a triangle whose angles add to 400 degrees on a flat sheet of paper. It is not that the universe intervenes to stop you building the apparatus. It is that the description of the apparatus, once you write it out fully in a space-time that contains that wormhole, does not describe anything. I understand that this feels like a dodge, and Novikov's critics have said exactly that. They call it a constraint with no mechanism, a rule with nothing enforcing it. His defenders reply that the demand for a mechanism smuggles in the assumption that something is being actively protected, and nothing is. There is no timeline being defended. There is only a set of configurations that satisfy the equations, and a much larger set that do not, and the second set does not happen for the same reason that nothing else which fails to satisfy the equations happens. Which is a strange thing to find yourself agreeing with, and yet it is difficult to say what is wrong with it. I find the philosophical shape of this genuinely unsettling, in a way the grandfather paradox never managed. The grandfather paradox is dramatic, and it is about you. This is quiet, and it is about the equations, and it says that, in a universe containing a closed time-like curve, the present would stop determining the future, not because the laws stopped working, but because they would start having more than one answer, and no preference between them. And notice what has happened to the objection. The grandfather paradox was, for most people, the reason the case was closed. It was not an intuition or a feeling, it was an argument, and it looked airtight. It was dismantled in 1991 in a mainstream journal by 3 physicists at Caltech, and the dismantling has stood for 34 years without serious challenge. Novikov's principle has a corollary that I think is the most quietly disturbing sentence in this whole subject, and I want to leave you with it before we take stock. The principle does not require that anything stop you. There is no mechanism, no guardian, no cosmic hand deflecting the bullet. The universe does not need a way to prevent you from killing your grandfather. It needs only that you did not. Part 7. What is left of the word? Let us stop for a moment and put the pieces on the table, because we are about halfway through, and it is worth seeing the shape of what has accumulated. We started with a sentence. Time travel is impossible. And we found that the sentence was carrying three separate claims, stacked, so that whenever one of them was challenged, the weight quietly shifted to another. The first claim was that you cannot move through time at a rate different from everybody else's. That one is not merely false, it is commercially exploited. There is a fleet of satellites over your head, running on clocks that were built wrong on purpose, detuned by 4.5 thousandths of a hertz on a workbench before launch. Because the people who build them accepted 100 years ago that time runs faster up there and designed around it. Every direction you have ever been given by a phone came out of a machine that treats time dilation as a manufacturing tolerance. That claim is gone, and it did not survive 20 minutes. The second claim was that the past no longer exists, so there is nowhere to arrive. And what we found is that this is not a claim physics makes. Relativity destroys the universal now, not as a philosophical flourish, but as a consequence of the measured constancy of light speed, with a formula attached and a number you can compute. Take one step toward Andromeda, and the moment out there that you are calling now slides by 4 days. The four-dimensional structure in which all of this is written contains your yesterday at its coordinates, and there is no privileged slice that says it has stopped. Whether that means the past is real in the full metaphysical sense is genuinely argued over. But the confident version of the objection, it is gone, it has been deleted, there is nothing there, is not something the physics supports. It is something we brought with us. The third claim was that going backward is forbidden. And what we found instead is 6 exact solutions of Einstein's equations, discovered over 70 years by people who mostly did not want them, every one of which contains paths that return to their own past. Einstein knew about the problem in 1915 and never solved it. Gödel handed him a universe full of the things as a birthday present in 1949, and Einstein, in print, conceded the point. And in all the time since, nobody has produced a theorem forbidding them. Not one. And the grandfather paradox, the argument almost everybody is actually relying on, the one that feels airtight, was taken apart in 1991 at Caltech with a billiard table. Not by finding a way around the contradiction, but by discovering that the contradiction never arises. Consistent histories exist, and the real trouble is that there are too many of them rather than none. So what is left? 2 things. Exactly 2, and I want to name them now, so you know where the rest of the night is going. The first is a bill. Every one of those 6 roots needs matter of a kind we know exists and cannot make in quantity. Matter with negative energy density, which is a real, measured, laboratory phenomenon, and also one of the most tightly rationed things in the universe. The numbers involved are large and specific, and we are going to go through them. The second is a conjecture. One paper, published in 1992 by the most famous physicist of the late 20th century, arguing that quantum effects will destroy any time machine at the moment it switches on. That paper is the reason the mainstream position is no, and I have already told you what the word conjecture means, and I am going to hold you to it. Now, both of those survivors are real, and I am not going to wave them away. But both of them are weaker than they sound, and one of them is weaker in a way that almost nobody outside the field knows about. There is a theorem from 1997 which shows that the argument in Hawking's paper cannot actually be evaluated at the exact place where it matters most. We will get there. It is worth noticing, while everything is laid out like this, how the character of the obstacle has quietly changed underneath us. We came in believing there was a rule. Somewhere in the equations, a prohibition with a proof attached. What we have arrived at, halfway through, is a price and a suspicion. Neither of those is nothing. Both of them are the kind of thing that has been wrong before, and both of them are the kind of thing a person can go and check. Before we do, we have to go through the quantum side, because there is a widespread assumption that quantum mechanics is where this all finally gets shut down. That when you stop treating the ball as a ball and start treating it properly, the whole thing collapses. The opposite happened, and the way it happened is stranger than the paradox it replaced. Part 8. The fixed point that always exists. In the same year that 3 physicists at Caltech were rolling billiard balls into wormholes, a physicist in Oxford was doing the quantum version, and he got a result that is, in its own quiet way, one of the strangest things in the literature. David Deutsch is best known as one of the founders of quantum computing, and the paper is called Quantum Mechanics Near Closed Time-like Lines. It came out in 1991 in Physical Review D, Volume 44, page 3197, and the approach he took to it is characteristic of him. Instead of asking what a particle does on a closed time-like curve, he asked what a computation does. Think of it as a circuit. A quantum system goes into the loop, comes back out at an earlier point, and interacts with its younger self. The interaction is described by some ordinary unitary operation, nothing exotic, just the normal machinery of quantum mechanics. The consistency requirement is that the state of the system arriving from the future has to match the state that the interaction produces and sends into the future. Whatever goes round has to be whatever comes round. In the language of mathematics, that is a demand for a fixed point. You have a map that takes a state to another state, and you are asking whether there is a state the map leaves unchanged. And here is where Deutsch's argument becomes remarkable, because there is a theorem about fixed points. It is Brouwer's fixed point theorem. It dates from 1911, and it is the same result that guarantees that if you stir a cup of coffee, at least one point in the liquid ends up exactly where it started. Applied to the space of quantum states, which is a compact convex set, exactly the sort of object Brouwer's theorem is about, it guarantees that a fixed point exists. Always. For any interaction whatsoever, including the one where the older system's whole purpose is to prevent the younger one from entering the loop. Take a second with that. The grandfather paradox, done properly in quantum mechanics, is not merely resolvable in some cases. There is a theorem that says a self-consistent solution exists in every case. Not sometimes, not usually, always, unconditionally, by a 114-year-old result about continuous maps. The way it works in practice, for the quantum grandfather setup, is that the fixed point turns out to be a mixed state, a 50-50 statistical mixture of the two outcomes, which reproduces itself perfectly through the interaction. The system emerges half killed and half not, in a way that feeds back exactly the input required to produce half killed and half not. It is consistent. It is also not remotely what anyone was hoping for. There is a detail here that ties this back to the billiard table, and it is a satisfying one. Brouwer's theorem guarantees that a fixed point exists. It says nothing whatsoever about whether the fixed point is unique. And in general, for these systems, it is not. There are typically many states that reproduce themselves through the interaction, and the physics gives you no way to prefer one. Which is exactly, precisely, the failure that Echeverria, Klinkhammer, and Thorne found with brass balls on green baize, 2 entirely separate pieces of work, one classical and one quantum, done in the same year by people working on different continents, and they broke in the same place, not at consistency, at uniqueness. When 2 independent approaches to a problem fail in the identical way, that is usually the theory telling you something about its own structure, rather than about your method. And the price is severe, which Deutsch was entirely upfront about. The evolution that comes out of his model is non-linear. That word is doing a lot of work. Quantum mechanics is linear. It is one of the deepest and most reliable structural facts about the theory. The thing that makes superposition work at all, the thing that means the whole, is exactly the sum of the parts. Deutsch's closed time-like curves break it, And once linearity goes, a series of things that quantum mechanics absolutely forbids become possible. You could clone an unknown quantum state, which the no-cloning theorem rules out. You could perfectly distinguish two non-orthogonal states, which ordinary measurement cannot do. Unitarity, the conservation of probability, the thing that makes the numbers add to 1, stops holding. And you could compute things you should not be able to compute. Scott Aaronson and John Watrous worked this out in 2009, and the result is that a computer with access to a closed time-like curve could solve any problem in a complexity class called p-space in polynomial time. To give you a sense of what that means, it would make classical and quantum computers exactly equally powerful, both of them at a level far above anything either can do now, and it would casually dispose of essentially every hard problem in computer science. Which is, depending on your temperament, either an argument that closed time-like curves cannot exist, or the single best reason to want one. Deutsch's is not the only model. Seth Lloyd and colleagues proposed an alternative, built out of quantum teleportation and post-selection, in which the loop is simulated by preparing entangled pairs and simply discarding every run in which the outcome would have been inconsistent. Their version is linear, which is a considerable virtue, and it handles the grandfather scenario differently. It does not resolve the paradox with a mixed state. It forbids the setup outright. The two models make different predictions in identical situations, which means that if you ever had a real closed time-like curve, you could tell them apart experimentally. This is a genuinely strange thing to be able to say about a subject with no data, except that there is a little data, not much, and I am going to be careful about what it is. In 2014, Martin Ringbauer, Matthew Broom, Casey Myers, Andrew White, and Alessandro Fedrizzi at the University of Queensland published a paper in Nature Communications, Volume 5, Article 4145, titled Experimental Simulation of Closed Time-like Curves. They generated pairs of single photons by shining a laser through a nonlinear crystal, encoded qubits in their polarization, and built an optical circuit whose input-output behavior is mathematically identical to a qubit interacting with an older version of itself under Deutsch's model. What I need to say clearly, because this experiment gets misreported constantly, is that nothing traveled backward in time. No causality was violated. No photon met its own past. What was built was a circuit with the same algebra, the same equations describing what comes out for what goes in. It is a simulation in the strict sense. And within that limit, it worked. The circuit found the fixed points. It reproduced the nonlinear behavior Deutsch's model predicts. It handled the case that people find hardest to think about, the unproved theorem scenario, where a computation's own output is fed back as its input, so that the answer justifies itself and nothing ever derived it, and produced the self-consistent result the mathematics requires. There is one more line of work worth naming before we move on. In December of 2024, Lorenzo Gavasino published a paper in Classical and Quantum Gravity arguing that closed time-like curve paradoxes dissolve for a completely different reason, thermodynamics. Anything traversing a loop, on his analysis, necessarily undergoes something called Poincare recurrence, and in doing so, its memory of the loop is erased. The history is consistent because nothing survives to carry the record of the inconsistency, whether that is a resolution or a very sophisticated way of changing the subject is being argued about right now. So the quantum door did not close. That is the thing to take out of this part. Everybody expected that when you did this properly, with the real theory rather than billiard balls, the whole subject would collapse. Instead, there is a theorem guaranteeing that consistent solutions always exist, a photonic experiment reproducing its mathematics, and a set of consequences so strange that the paradox we started with now looks positively comfortable. We are going to leave the loops for a while, because there is something else that happens to the past when you look at it quantum mechanically, and it does not require a wormhole, or a rotating cylinder, or an infinite amount of anything. It has been done on a laboratory bench, with a laser, hundreds of times. Part 9. The past that has not finished happening. In 1978, John Archibald Wheeler proposed an experiment that he did not think anybody would ever be able to perform, and which has now been performed several times, with photons and with atoms, and it does something very specific to the idea that the past is finished. Wheeler's setup starts from the oldest strange result in quantum mechanics. Send light through two slits, and you get an interference pattern, which is what waves do. Set up a detector to determine which slit each particle went through, and the interference disappears, and you get two clumps, which is what particles do. Whether you look decides what you see. Wheeler's question was, what if you decide after? Take an interferometer, a device that splits a beam into two paths and can recombine them. If the recombining element is in place, the two paths interfere, and you see a wave. If it is absent, each detector tells you unambiguously which path the particle took, and you see a particle. Now make the choice of whether to insert that recombining element only after the particle has already entered the apparatus and is somewhere in the middle of it. On the naive reading, the choice you make now determines what the particle was doing a moment ago, during a period that has already elapsed. For a long time, this was a thought experiment, because the timings are brutal. You need the switching to be genuinely later than the entry, verifiably, with no possibility of the particle somehow knowing in advance. In 2007, Vincent Jacques and colleagues at the École Normale Supérieure in Cachan published a near-ideal version in Science, volume 315, page 966. Their photons came one at a time from a single nitrogen vacancy defect in a diamond, genuinely single photons, not attenuated pulses that occasionally contain two. The interferometer arms were 48 meters long, and the decision about whether to insert the output beam splitter was made by a quantum random number generator, physically located so that its choice was space-like, separated from the photon's entry into the apparatus. Space-like separated means what it meant earlier tonight. No signal, not even light, could carry the news of the choice back to the entry point in time to matter. The photon could not have known. The results came out exactly as quantum mechanics says they should. Insert the beam splitter, and you get interference. Leave it out, and you get which path information. The choice, made after entry, determines which. In 2015, a team at the Australian National University, led by Andrew Manning, did the same thing with a single helium-4 atom released from a Bose-Einstein condensate, published in Nature Physics. Instead of mirrors, they used pulses of laser light forming standing wave gratings, and the second grating was applied, or not, after the atom had already passed through the first. A massive particle, with rest mass, something you could in principle weigh, behaving the same way. Wheeler had a cosmic version of this in mind, and it is worth pausing on because it takes the timescale from nanoseconds to something the human mind cannot hold. Imagine a quasar so far away that its light has been traveling for thousands of millions of years. Between it and us sits a galaxy, massive enough to bend the light around itself, so that photons from the quasar can reach Earth by two different routes around either side of that intervening mass. That is a two-path interferometer, with arms thousands of light-years apart, and it was assembled by gravity before the Earth existed. Point a telescope at it and choose, tonight, whether to combine the two beams and look for interference, or to look at each path separately. On the naive reading, the choice made tonight by a person with a coffee determines what light did during a journey that began before the sun formed. There is also a version that goes further than either, and it is not a thought experiment. In 2012, Xiao Song-ma and colleagues in Vienna performed delayed choice entanglement swapping. In that experiment, the decision about whether two photons had been entangled with each other was made after both of them had already been measured and destroyed. Not whether to measure them, whether they had been entangled, a property of a relationship decided after both parties to it were gone. Then there is the version that goes furthest, and I want to walk you into it slowly, because it is the one that does the real damage, and it is also the one that gets described most irresponsibly. Yoonho Kim, Rong Yu, Sergei Kulik, Yanhua Shi, and Marlon Scully published it in 2000 in Physical Review Letters, Volume 84, page 1. It is called the Delayed Choice Quantum Eraser. Stand at the apparatus for a moment. A laser hits a crystal and produces pairs of photons entangled with each other. One of each pair, call it the signal photon, takes a short route to a detector, arrives, and is recorded. A click, a number written into a file. That event is over in every ordinary sense of the word. Measured, logged, past tense, done. Its twin, the idler, is still traveling. It has been sent on a much longer path, meters of extra optical distance, and it will not arrive anywhere for some time yet. Eventually it reaches a beam splitter. That beam splitter has no memory and no intention and no knowledge of anything. It simply sends the photon one way or the other, at random. If it goes one way, the photon ends up at a detector that preserves the information about which slit the pair came from. If it goes the other, it ends up somewhere that destroys that information irrecoverably. Neither outcome touches the file. The signal photon's detection has already been written down. Nothing is going back to alter it, and nothing does. And yet when the experimenters take the file and sort those already recorded signal detections according to which idler detector fired afterwards, something appears. The subset of signal photons whose partners had their witch path information erased forms a clean interference pattern. The subset whose partners kept that information forms no pattern at all. The already recorded data falls into a shape that depends on a coin that had not yet been tossed when it was recorded. Now, the correction, and I am going to give it to you in full, because sundown science does not do this the sloppy way. No record was altered. Not one bit in that file changed. The interference pattern was not created retroactively. It was extracted, by sorting, from data that was already sitting there. And here is the detail that kills the popular reading stone dead. If you take the signal detections and do not sort them, if you just look at all of them together, there is no interference pattern whatsoever. The fringes in the one subset and the anti-fringes in the other are exactly complementary. They add up to a flat, featureless smear, which means you cannot use this to send a message backward, because to see the pattern at all, you need the idler data, and the idler data cannot reach you faster than light. Nothing has broken. Causality is intact. Relativity is intact. The experimenters say so in the paper. So what actually failed? What failed is smaller than time travel, and, I would argue, more unsettling. What failed is the assumption that there was a fact of the matter. You came into this with a picture of the past that you have probably never once articulated, because it never needed articulating. The picture is that, whatever happened, happened. That behind you there is a complete set of facts, fully determinate, every detail settled, and the only question is whether anybody bothered to write them down. Which slit did the photon go through? It went through one of them. Obviously, it might be unknown, but it is not undecided. Unknown and undecided are different words. That picture is not needed to describe these results. And worse, holding on to it produces contradictions. There is no consistent assignment of a definite path to each photon that reproduces what the detectors record. The path was not unknown. There was nothing there to know. Sit with that for a second, because it is doing something quite specific to your sense of what is behind you. Everything you assume about the past, that it is complete, that it is settled, that it is a finished object sitting there whether or not anybody consults it, is an extrapolation from ordinary experience up into a domain where it stops working. Nothing dramatic happens when it stops working. No paradox, no violation, no light show. It simply turns out that the universe never made the commitment you assumed it had made, and got away with it, for the entire history of the world, because nobody thought to check. It is worth knowing that Wheeler himself, who designed the whole thing, refused to read it the way it is popularly read. He was firmly against any suggestion of influence running backward. His position was that no phenomenon is a phenomenon until it is a registered phenomenon, and that asking what the photon was doing in between registrations is not a hard question, but a meaningless one, like asking what color a number is. The man who built the experiment thought the interesting result was not that the past had changed, but that there had never been a past of that kind to change. I want to be very careful here about what I am not saying, because this material is routinely abused. I am not saying the future changes the past. It does not. I am not saying you can influence what has already occurred. You cannot. And I am not saying this is a mechanism for time travel, because it is not one. What I am saying is narrower. The second claim, that the past is gone and there is nowhere to arrive, quietly assumed a particular kind of past, a completed one, a finished ledger. Relativity already took away the idea that the ledger is closed at any universal moment, and quantum mechanics, from a completely different direction, in an entirely unrelated set of experiments, using nothing more exotic than a laser and a crystal and a lot of patience, has taken away the idea that the entries in it were all filled in. Part 10. The physics of influence that runs backward. There is a word that gets used to dismiss things, and it turns out to have a respectable literature behind it, and I think the discovery of that literature is one of the more disorienting experiences available to a curious person. The word is retrocausality. Say it in ordinary company, and you will get a particular expression, the polite one people reserve for crystals and pyramids. And yet there is a steady, serious, 60-year line of work in the foundations of quantum mechanics on precisely this, published in the Proceedings of the Royal Society and Physical Review Letters, by physicists at Tel Aviv and Cambridge and Oxford. And the reason it exists is not that anybody wants time travel. The reason it exists is that it might fix something. Let me start where it starts. In 1964, Yakir Aharonov, Peter Bergman, and Joel Lebowitz published a rule about quantum probabilities. Ordinary quantum mechanics tells you, given how a system was prepared, here are the odds for what you will measure. It conditions on the past. That is the only thing we ever ask it to do, and the asymmetry feels like a feature of the theory. Aharonov and his colleagues asked what the formalism looks like if you condition on both ends, if you specify how the system was prepared and also how it was found later, and then ask about a measurement in between. What comes out is a formula that is perfectly symmetric between the initial state and the final state. The past and the future enter it in exactly the same way, with exactly the same mathematical role. The asymmetry, in other words, was not in the theory. It was in the question we were habitually asking. That result is the seed of what became the two-state vector formalism. In it, a quantum system between preparation and post-selection is described by two states, one evolving forward from the beginning and one evolving backward from the end. Both are needed. Neither is more real than the other. And this is not poetry. It is a calculational framework, and it produces correct predictions, and people use it to design experiments. The most famous thing to come out of it has one of the best titles in the history of physics. In 1988, Aharonov, David Albert, and Lev Vadman published a paper in Physical Review Letters, Volume 60, page 1351, called How the Result of a Measurement of a Component of the Spin of a Spin 1/2 Particle Can Turn Out to be 100. A spin 1/2 particle has two possible spin values along any axis, +1/2 and -1/2. That is the entire menu. The paper's title announces a measurement returning 100. The trick is what they call a weak measurement. Instead of coupling your instrument strongly to the system and getting a definite eigenvalue with a bang, you couple it very gently, so gently that any single run tells you almost nothing and barely disturbs the system. Do that many times on an ensemble that has been both prepared in one state and post-selected in another, average the results, and the number you get, the weak value, can sit far outside the range of anything the operator is supposed to be able to return. Now there is a long and unresolved argument about what a weak value is. Some say it is a real property of the system between the two selections. Others say it is an artifact of statistics and post-selection, and means nothing ontological at all. That fight is live. What is not in dispute is that the formalism buys you something. In 2008, Onur Hostin and Paul Kwiat used weak measurement amplification to detect a beam displacement of about 1 ångström, the width of an atom, and published it in Science. That is not an interpretive flourish. That is a laboratory technique that measures things other techniques cannot reach. Whatever the two-state formalism is describing, it is not describing nothing. There is one more result from this tradition that I cannot leave out, because it is the strangest object in the whole cabinet. Aharonov and colleagues proposed it in 2013, and it was realized with neutron interferometry the following year, and it is called the quantum Cheshire cat. Take a neutron. A neutron has a magnetic moment, a property of it, in the same way that your weight is a property of you. Prepare the neutron in one state, send it through an interferometer, and post-select on another state, and the weak measurements report that the neutron went down one arm of the apparatus, while its magnetic moment went down the other. The particle in one channel, one of its own properties in the other. Whether that is what is happening, or whether it is an elaborate statistical artifact of the post-selection, is exactly the argument I mentioned a moment ago, and it is still running. But the name is apt. Lewis Carroll's cat vanishes and leaves its grin behind, and Alice remarks that she has often seen a cat without a grin, but never a grin without a cat. She had not been to Vienna. It is also worth noting the chronology, because it inverts what most people assume. The Aharonov-Bergman-Leibovitz rule appeared a matter of months before Bell's theorem. The time-symmetric formulation of quantum probability is not a later patch, invented to escape Bell's conclusion. It was already there when the conclusion arrived. So why do serious people take the retrocausal reading seriously? Not for the romance, for Bell. Bell's theorem is the most important result in the foundations of quantum mechanics, and what it establishes is that no local hidden variable theory can reproduce quantum predictions, a result confirmed experimentally to an extraordinary degree and honored with the Nobel Prize in 2022. The usual conclusion is that the world is non-local. Something about it is connected in a way that does not respect distance. But Bell's proof rests on assumptions, and one of them is easy to miss. It assumes that the settings the experimenters choose, which way to orient the detectors, are statistically independent of the hidden variables describing the particles. That sounds so obviously true that it barely looks like an assumption. Of course, my free choice of detector angle has nothing to do with what the particle was carrying when it left the source, unless the future setting can influence the past variables, in which case the assumption fails, and Bell's theorem does not apply, and you can have a hidden variable theory that is perfectly local and still reproduces every experimental result. That is the prize. Retrocausality is not attractive to these physicists because it sounds exciting. It is attractive because it would let the world be local again, and locality is something physicists give up very reluctantly. The line of work runs back a long way. Olivier Costa de Beauregard proposed a version in 1953, 11 years before Bell's paper even existed, as a response to the Einstein-Podolsky-Rosen argument. John Cramer's transactional interpretation came in 1986, built on waves running in both temporal directions. Hugh Price argued through the 1990s that any genuinely time-symmetric account of the world has to be retrocausal. Ken Wharton and Nathan Argaman have developed approaches that start from the Lagrangian, which is naturally symmetric in time, rather than from an evolving state. And in 2017, Matthew Leifer and Matthew Pusey published a paper in Proceedings of the Royal Society A, volume 473, with the title, Is a Time-Symmetric Interpretation of Quantum Theory Possible Without Retrocausality? They prove that the answer is no. From an operational assumption about time symmetry, plus a technical condition they call lambda mediation, they derive that any time-symmetric account of quantum theory must involve influences running backward. You can have time symmetry, or you can have no retrocausality. You cannot have both. And now the counterweight, which belongs here as much as the result does. Tim Maudlin, one of the most formidable philosophers of physics alive, has argued that the central proof contains a fatal error and that the conclusion is not established. The result is contested. I am not going to tell you it stands. I also want to be extremely clear about the ceiling on all of this, because it is a low one. Retrocausality in this technical sense means influence on hidden variables, on whatever underlying description, if any, sits beneath the quantum state. It does not mean you can send a message backward. No signaling holds throughout every one of these frameworks. There is no version of this in which you learn tomorrow's lottery numbers, and the people who work on it are the first to say so. So this is not a route. Nobody is going to build anything out of it. What it is a second independent line of attack on the same assumption. We have spent this half of the video circling one idea from two directions. Relativity says there is no universal moment at which the past becomes past. The delayed choice experiments say the entries in the past were not all determinate, and now the time-symmetric formalism says that the deepest description of a quantum system may be one in which the future is written into it as inescapably as the past is. Three different pieces of physics, developed independently, none of them about time travel, all of them chewing on the same assumption from different sides. And the assumption is the one we identified 2 hours ago as the real objection. Not that the journey is hard, that there is nowhere to arrive. Part 11. The Bill. Everything so far has been about removing objections. This part is about the objection that stays, and I want to give it to you at full strength, because it is a good one, and because a video that only knocks things down is not worth 2 hours of anybody's night. Here is the shape of it. Every one of those 6 routes to the past requires a specific kind of matter, and we cannot make it in the amounts required. Not because our technology is primitive, because the universe appears to ration it. Start with what a wormhole actually is. In 1988, Michael Morris and Kip Thorne published a paper in the American Journal of Physics that was written, remarkably, as a teaching exercise. Thorne had been asked by Carl Sagan for a scientifically defensible way to move a character quickly across the galaxy in a novel he was writing. The novel became Contact, and Thorne found himself doing something physicists rarely do. He worked backward. Normally in general relativity, you specify the matter and calculate the geometry. Thorne and Morris specified the geometry they wanted. A tunnel, held open, no horizon, survivable tidal forces, and calculated what matter would be required to produce it. The answer came back immediately and unambiguously. To hold a wormhole throat open, you need matter that gravitates the wrong way, not merely light matter or unusual matter, matter whose energy density, as measured by a beam of light passing through the throat, is negative. In technical language, it must violate the averaged null energy condition. In plain language, the throat needs something that pushes space apart rather than pulling it together, and that is not what any known substance does. That is also, from later work, precisely what Alcubierre's warp bubble needs in its walls, and what Hawking argued a finite Tipler cylinder needs. The requirement keeps reappearing at the end of every route, like a toll booth that has been quietly installed on all 6 roads. Now, here is where it stops being a simple no. Negative energy density exists. It is not hypothetical, it is not a mathematical fiction, and it has been measured. In 1948, Hendrik Casimir predicted that 2 uncharged conducting plates held very close together in a vacuum would attract each other, because the vacuum between them can only support certain wavelengths of quantum field fluctuation, while the space outside supports all of them. Fewer fluctuations inside than outside means the region between the plates has less energy than empty space, which is to say, its energy density is negative. Steve Lamoureux measured the force in 1997 and got agreement at about the 5% level. Umar Mohideen and Anushri Roy tightened it to about 1% the following year. Squeezed states of light also carry locally negative energy density, and those are made routinely in optics laboratories. So the exotic matter is real. The problem is the quantity. The Casimir energy density between plates, separated by a micrometer, is of order -1 10,000 millionth of a joule per cubic meter. That is a large number by the standards of vacuum physics, and an entirely negligible one by the standards of anything you might want to build. The force it produces between 2 plates a micrometer apart is roughly the weight of 1,000th of a housefly per square centimeter. And it gets worse than scarcity, because quantum field theory does not merely make negative energy rare, it constrains it with a formula. They are called the quantum inequalities, worked out principally by Larry Ford and Tom Roman through the 1990s. And what they say is this: the more negative an energy density is, and the longer it lasts, the more tightly it is bounded. Specifically, the time-averaged energy density along an observer's path is bounded below by a constant divided by the 4th power of the averaging time. Negative energy always arrives, escorted by compensating positive energy nearby. It cannot be concentrated arbitrarily, and it cannot be held for long. The universe appears to lend it and want it back. In 1996, Ford and Roman applied their own inequalities to wormholes, and the result is the single most quoted number in this subject. The shell of exotic matter at the throat cannot be thicker than roughly 10 to the -21st meters, times the throat radius in meters. For a throat 1 meter across, that is a shell about 10 to the -21 meters thick. A proton is about 10 to the -15 meters across. So the requirement is a shell of negative energy matter roughly a millionth the width of a proton, wrapped around a 1 meter tunnel, held in place. Notice what kind of problem that is. It is not that you need a great deal of exotic matter, it is that you need it arranged with a precision that has no analogue anywhere in physics or engineering. 2 clarifications before we go on, because both of these get garbled constantly, and both of them matter. The first is that exotic matter is not antimatter. This confusion is everywhere, and it is completely wrong. Antimatter has ordinary, positive energy density. An antiproton weighs the same as a proton and falls the same way. That was directly confirmed at CERN in 2023. Antimatter is difficult to make, and spectacular when it annihilates, and it is entirely useless for holding a wormhole open. What is needed is something with negative energy density, and antimatter is not it. The second is about the wormhole's size, and it makes the shell requirement worse rather than better. Morris and Thorne calculated the tidal forces on a body passing through the throat, and to keep them survivable, comparable to what a person experiences standing on Earth, rather than what they would experience being stretched into a filament, the throat has to be big, kilometers across on their estimate, which means the exotic shell scales up with it, while the thickness constraint scales with it too, and the arrangement precision required goes from absurd to considerably more absurd. There is one genuine crack in the wall, and intellectual honesty requires putting it in. The average null energy condition, the specific rule that all this violates, has been proven for free quantum fields in flat spacetime. Gunnar Klinkhammer did that in 1991. And for a class of cases in curved spacetime by Noah Graham and Ken Olam in 2007. It has never been proven in general for a curved background with interacting fields, which is the case that actually applies to the real universe. It is widely believed to hold there. It is not known to. The warp drive has a similar history, and it is more interesting than the popular version. Alcubierre's original 1994 solution required negative mass energy of order 10 to the 64th kilograms for a bubble a few hundred meters across, more than the mass energy of all the ordinary matter in the observable universe, by something like 11 orders of magnitude. That number is where the drive's reputation comes from. But it did not stay there. Chris van den Broek showed in 1999 that changing the bubble's topology, a very small outer neck opening into a large interior, cuts the requirement by dozens of orders of magnitude. Alexei Bobrik and Gianni Martire produced a general class of subluminal warp solutions in 2021. Eric Lentz that same year, and Sean Fell and Lavinia Heisenberg alongside him, claimed soliton solutions requiring only positive energy. And then, in 2022, Jessica Santiago, Sebastian Schuster, and Matt Visser went through those claims carefully and argued that the positive energy solutions still violate the energy conditions when the analysis is done properly. And there is a pattern in that history, which is the honest conclusion of this whole part. In 2024, a constant velocity warp solution was published that genuinely does satisfy all the energy conditions. It is also strictly subluminal, slower than light, and therefore has no time travel implication whatsoever. Every time somebody gets the energy conditions satisfied, the causality violation quietly disappears. Every time the causality violation survives, so does the exotic matter requirement. There is one attempt that deserves naming for reasons that are not technical. Ronald Mallet is a physicist at the University of Connecticut who has spent a large part of his career on a proposal to use a circulating ring laser to drag spacetime around into a closed time-like curve. He has been open about where the project came from. His father died of a heart attack when Mallet was 10 years old, and he read The Time Machine the following year, and he has never really stopped. In 2005, Ken Olam and Alan Everett published a critique showing that the energy required is unattainable, and that the solution as presented contains a singularity. The critique appears to be correct. I do not think it makes the story less worth telling. So that is the bill. It is enormous, it is specific, and it is calculated in real units by people who checked each other's arithmetic. And it is a bill, which is not the same thing as a rule, and everything now depends on whether there is a rule. Part 12. The Conjecture. On the 15th of July 1992, Physical Review D published a paper by Stephen Hawking, running from page 603 to page 611 of volume 46. It is the single most cited reason that physicists say no to this question, and it is the reason the popular consensus exists at all. The title of the paper is Chronology protection conjecture. I have been holding that word since part 5, and now I want to spend it properly, because it is not an accident, and it is not modesty. Hawking was one of the most confident people ever to work in this field. He bet on black holes, and paid up in public when he lost. He was not a man who hedged for the sake of hedging. He used the word conjecture, because that is the word for what he had. Here is the argument, and it is a good one. Suppose you build a time machine, a wormhole with offset mouths, say. There is a moment, a surface in space-time, at which the first closed time-like curve appears. Physicists call it the Cauchy horizon, or in this context, the chronology horizon. It is the boundary between the region where the past is still safely behind you and the region where it is not. Now think about what happens to the quantum vacuum near that boundary. The vacuum is not empty, it is full of fluctuations, and those fluctuations propagate. Near the chronology horizon, there are light paths that very nearly close on themselves, that come back almost to where they started. A fluctuation travelling on such a path can go round and round and round again, and each circuit adds to the energy density at that location. Hawking calculated what this does to the renormalized stress-energy tensor of a quantum field as you approach the horizon. It diverges. It runs to infinity. And in general relativity, energy density is what creates curvature. So an infinite energy density, at the moment the machine would switch on, means the geometry tears itself apart first. The time machine destroys itself at the instant of its own creation. His summary line, which has been quoted 10,000 times since, is that the laws of physics conspire to prevent time travel on a macroscopic scale and thereby make the universe safe for historians. It is a beautiful argument, and Hawking himself flagged, in the paper, that it could not be completed, that a genuine proof would require a theory of quantum gravity, and that he did not have one. Now let me tell you the part that almost nobody outside the field knows. In 1997, Bernard K., Marek Radzikowski, and Robert Wold published a paper in Communications in Mathematical Physics, volume 183, page 533. It concerns quantum field theory on spacetimes with a compactly generated Cauchy horizon, which is to say, exactly the situation Hawking was analyzing. They prove two theorems. What the theorems establish is that at certain points on the horizon, the past terminal accumulation points of the horizon generators, which is a mouthful, but which is precisely where the almost closed light paths pile up. The two-point function of the quantum field is ill-defined. Read that carefully, because the difference between this and Hawking's result is the whole ballgame. Hawking's argument says the energy density becomes infinite. K., Radzikowski, and Wold show that at the decisive points it does not have a value at all. Not a large value, not an infinite one, no value. The mathematical object you would need in order to ask the question cannot be constructed there. The framework does not answer the question. It stops being able to state it. The authors themselves present this as support for chronology protection, and that reading is defensible. If your theory breaks down when you try to build a time machine, that is at least suggestive. But what the theorems establish directly is that semi-classical gravity, the framework in which Hawking's divergence argument lives, is not competent to settle the matter at the exact spot where the matter is settled. You cannot use a calculation to prove something at a point where the calculation is undefined. And there are counterexamples inside the framework. In 1998, Li-Shin Lee and Richard Gott found a self-consistent vacuum state in which the stress-energy tensor stays finite on the chronology horizon in Misner space. Sergei Krasnikov and others have argued that the divergence is not generic and depends on the field content and the topology of the spacetime you happen to have chosen. Matt Visser, who has written the most thorough surveys of the subject, summarizes the state of things in a phrase that has been quoted in almost every review for 20 years. The chronology protection conjecture is extremely reasonable, and there is no theorem. I want to say the thing I promised in part 5, now that you can see what it applies to. He called it a conjecture. He put the word in his own title, in the journal, where it has sat for 33 years. And a conjecture is a sentence with a question mark hidden somewhere inside it, no matter how many times it gets repeated without one. The honest position, the one held by most working relativists, and it is a perfectly respectable one, is that quantum gravity will almost certainly forbid this, and that the classical solutions are artifacts of running a theory past the edge of its own validity. That may well be right. I would probably bet that way myself if forced. But notice the structure of the bet. It is a prediction about what a theory that does not yet exist will say, when it is written, by somebody who has not yet written it. Every serious candidate for quantum gravity, string theory, loop quantum gravity, causal sets, asymptotic safety, is either incomplete or untested, or both, and none of them has produced the chronology protection theorem, not for lack of interest. It would be a famous result. Which brings me to the 28th of June, 2009. Picture a room at Gonville and Caius College, Cambridge. There is champagne on ice. There are balloons. There is a banner across the wall that reads, "Welcome Time Travelers." And there is Stephen Hawking, sitting in the room, waiting. The invitation gives the coordinates precisely, latitude, longitude, the date, the time. Because if you are inviting someone from the future, you had better be specific. Nobody comes. The invitations went out the following day. That was the design. Hold the party first. Publish the invitation afterwards, so that only somebody travelling backward could possibly attend. Hawking called it experimental evidence for chronology protection, and he was smiling when he said it, and he was also not entirely joking. Hold on the empty room for a moment, because there is something genuinely poignant in it. This is a man who spent 17 years arguing that the laws of physics conspire to keep the past closed, and the only experiment anybody has ever run on the question is him, in a decorated room with the champagne going warm. And the result he got is the weakest kind of evidence that exists, an absence from a search with an unknown and quite plausibly zero prior probability of success. He knew that. He ran it anyway. That is what the strongest case for no actually consists of. A conjecture that requires a theory nobody has. A semi-classical argument that a theorem proves cannot be evaluated at the critical point. Counterexamples that have not been dislodged. And an empty room in Cambridge. I should say something about the other kind of story, briefly, because it circles this subject constantly, and it deserves a straight answer. There is the Philadelphia experiment, which traces entirely to a set of letters written in the 1950s, whose real substrate is degaussing, running current through a ship's hull to hide it from magnetic mines. There is the Montauk project, attached to a genuine Cold War radar installation, and to nothing else. There are the photographs, which turn out to show sunglasses and sweaters that were on sale in 1941, and hearing aids. There are patents, and a patent is not a working device. The office does not test whether the thing runs. What interests me is the direction of the error. Every one of those stories assumes the difficult part is building the machine, and that somebody is hiding the answer. The real physics says the difficult part is sourcing a stress-energy tensor that no known matter produces, and nobody is hiding anything. It is in Physical Review D. It has been there for 33 years. The scandal they are reaching for exists. General relativity really does permit paths to the past, and hardly anyone knows it, and it is published rather than concealed. So we have arrived. Every objection is on the table, and every one of them has been weighed, which means it is time to answer the question we started with. Part 13. 3 claims, and only one of them left. So here is the answer, and it is not a loophole, and it is not a wormhole, and it is not something anybody discovered last year. Time travel is not as impossible as you think, because the word impossible was carrying 3 claims, and only one of them is still standing. The first claim was that you cannot move through time at a rate different from everybody else's. That one is a manufacturing tolerance. There are satellites over your head, right now, running on clocks that were built wrong on purpose, detuned on a workbench by 4.5 thousandths of a hertz, wrong at sea level and right in orbit. And they have been correct for 30 years, because the engineers accepted 100 years ago that time is not the same everywhere and designed around it before breakfast. Sergei Krikalev is 0.02 of a second younger than the rest of us and can be asked about it. That claim is not merely false, it is commercially exploited. The second claim was that the past no longer exists, so there is nowhere to arrive, and that one is not a finding of physics. It is an intuition, an extremely strong one that everybody has, one that feels like part of the furniture of the world, rather than a position anybody chose. And it is the intuition that relativity contradicts more directly than almost anything else it touches. There is no universal now. Take one step toward Andromeda, and the moment out there that you are calling the present slides by 4 days. Your yesterday sits at its coordinates in a 4-dimensional structure, and somebody moving differently to you, somewhere, has it inside their present tense. And from a completely different direction, in experiments that have nothing to do with any of this, quantum mechanics has taken away the idea that the entries in that past were all filled in to begin with. The objection was never that the journey is hard. The objection was that there is nowhere to arrive. And of everything we have looked at tonight, that is the one physics is least willing to agree with. Which leaves the third claim. And the third claim is genuinely open. I said I would be honest with you about that at the start, and I have not changed my mind. But its status is not forbidden. Its status is conjectured to be forbidden, by an argument whose author put the word conjecture in his own title, which requires a theory of quantum gravity that nobody has, and which a theorem from 1997 shows cannot be evaluated at the one point where it needs to be, against 6 exact solutions of Einstein's equations that are already written down, already published, already sitting in the journals, containing paths that return to their own past, and with a bill attached, a genuinely enormous bill, denominated in a kind of matter we have measured in the laboratory and cannot produce in quantity or arrange with the required precision. Impossible, unaffordable, and unproven are 3 different words. Only one of them was ever a law. And the grandfather paradox, the thing almost everybody is actually leaning on, the argument that feels airtight, the one that seems to settle it by pure logic, without needing any physics at all, was taken apart in 1991, twice, independently, on 2 continents, not by finding a clever way around the contradiction, by discovering that the contradiction never arises. Consistent histories exist. There are, if anything, too many of them. It is worth naming, plainly, what is actually unknown, because a list of open questions is a more useful thing to carry away than a verdict. We do not know whether a theory of quantum gravity forbids closed time-like curves, because we do not have a theory of quantum gravity. We do not know whether the averaged null energy condition holds in general, in a curved spacetime, with interacting fields, which is the only case that describes the real world. It is proven in special cases and assumed in the rest, and the assumption is doing an enormous amount of load-bearing work. And we do not know what happens to determinism in a universe where the initial conditions admit infinitely many futures, which is what the billiard ball result actually established, and which nobody has since explained away. 3 open questions, each of them the kind of thing a person could spend a career on. None of them the question people think is settled. There is also a quieter fact about the shape of the field that I think is worth having. 3 positions are held by serious people, and they do not reduce to 2. There are those who think quantum gravity will close the door. There are those who think the door is open, and the doorway is unaffordable, possibly permanently. And there are those who think the door is open, the histories are constrained to be consistent, and that this is not a strange, special rule, but exactly what physics has always said about everything, that the world does what satisfies the equations and nothing else. Those 3 groups are not arguing about the evidence. They agree about the evidence. They are arguing about what it is evidence of. I said at the start that the reason would not be the one you were expecting, and I think that is what it comes to. You probably came in expecting either a debunking or a promise, either a physicist explaining patiently why it cannot be done, or somebody selling you a wormhole. What is actually there is neither. What is actually there is that the question was never settled, that the settling was something we did ourselves, out of a mixture of good instinct and a paradox that turned out not to be one, and that the professional literature has been quietly disagreeing with us in public for 70 years. I do not know whether anyone will ever go anywhere. I would guess not, and most physicists would guess not, and the guess is reasonable. But it is a guess, and it is worth knowing that it is one. And there is one more thing I want to leave you with, gently, because it is the part that has stayed with me. If the block picture is right, and it might not be, and the argument about it is 120 years old and still running, then nothing that has happened has stopped happening. Every moment you have lived through is at its coordinates in that structure, permanently, in the same way that the far end of a road is still there when you are standing at this end of it. Not preserved, not remembered, just there, being what it is, at its own address. Einstein wrote something like that in a letter, 4 weeks before he died, to a family who had just lost somebody he loved too. He said that for those of us who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. He was not being poetic. He was describing the geometry of his own theory to people who needed it to be true. Whether it is true is exactly what remains open. Whether anything could ever reach across that structure is more open still, and will stay open until somebody writes down a theory of quantum gravity and works out what it says. But the next time somebody tells you that the past is gone, you might find yourself wanting to ask them a question. Gone according to whom? Cutting at what angle? Moving at what speed? Because there is a version of that answer, published, uncontested, and 117 years old, in which the past is not gone at all. It is simply somewhere we do not know how to reach.